Hello and welcome to the Wireless Power Transfer Advanced Coil Knowledge presentation today. My name is Jem Som. I'm responsible for the Wireless Power Transfer department at Würth Elektronics, and I would like to present you today some inside views about our wireless power coils. Today's agenda is very simple. We have some examples and applications. I would like to explain you a little bit about the coil physics and what kind of materials have an impact on it, and for sure the coil tuning, and in the end a little bit to show you what is possible to customize. Applications. Beside these very well-known consumer products in the market, we have different kind of other products. This could be in the automotive area, like we can see here in the picture. It's a BMW charging plate to charge a whole mobile or whole car. Or you can also charge your mobile any kind of infrastructure or furniture, like you will have it on trains, airports, in the plane itself, for example, or at home or in the office. Additionally, in the medical area, there are possibilities which could be used in the implants in the body, or also chargers which are able to charge some kind of other applications in or around the human bodies. Last but not least, in the industrial area, there are rough, harsh areas and applications possible, which are, for example, underwater, and the applications must be sealed that you can use it in very harsh environments. As an example, I would like you to show today also a customer of us, which are using an hearing aid for a sound processor. This sound processor is also completely sealed and will be placed with a magnet on your head, which is activating a sound processor. And this sound processor is developed for people which cannot hear or not able to hear. In this case, the sound processor is enabling the cochlear implants and transferring data and, for sure, energy. But also the consumer branch is important, for sure. In this case, as an example, we will have the iPhone 8 and the iPhone 11 here, some pictures. As you can see, the size of the coil is a very big key for the success. As from the user experience, we don't want to search the charging point if I would like to charge my mobile at the charging station. No, I just want to put it on top. It should be charging immediately. And how this works and how we can get a very good performance. In this case, to understand how we can influence it, we would like to dive in a little bit in the coil physics. The coil physics, for sure. A coil or inductor can be explained in a simple way. You can have a single conductor, which we can see here in the picture, and the single conductor, if a current is flowing through it, you will see the magnetic field around this single conductor. Now, if you use the single conductor and make some windings, you will have an air coil. The air coil, which is shown here in the picture with current, is flowing through these windings. The magnetic field will be inside of this air coil. How we can improve it additionally? If we use a rod core. The rod core is the same air coil as before, but the red material is a ferromagnetic material, which is focusing and increasing the magnetic field inside the coil. And this will end up in a formula. And this formula are based on the material. As mentioned before, the material can be iron powder, nickel zinc, manganic zinc, or metal alloy. All these different materials are defined by the permeability factor. Additionally, the area is important to calculate the inductance. On top, as mentioned before, I have to have different kind of windings inside of the used area. And in the end, the effective field length, which is shown here in the rod core, in the ring core, and this ring core effective length area is this black arrow. In the end, the inductance will be calculated from the permeability multiplied by the magnetic area multiplied by the turns in square and the effective field length divided. This kind of coil itself will not be used as for wireless power. We need two coils. These two coils are used in a wireless power transfer system. This transfer system, we will have a primary side and a secondary side. It's like a transformer with a big air gap. And these two primary and secondary sides are coupled with a K factor. In the middle, we have two coils, primary and secondary, or transmitter and receiver coil. They have an air gap and a distance D. A coil, a transmitter or receiver coil, can be transferred the energy from the kilohertz range and in a short distance, as we are looking here inside of a closed coupled system. What is important? In the end of the day, we would like to have a very high efficiency. The high efficiency is defined by this formula. This formula is very complicated, but we can see that important is that if the K factor and the Q factor are very high, the efficiency is also high. So the coupling constant and the quality factor are defining the maximum efficiency of a system. If you have a look at the different kind of Q factors of a system, we can see here in this diagram that all different kind of Q factors, as bigger they are, the efficiency is bigger and the coupling is getting better. So that means the coupling is often limited by the system itself because of the receiver and transmitter system are defined by the housing, by the application itself, as we've seen before, as a mobile or iPhone. The Q is depending on the transfer distance and of the misalignment of the system. If we go to the misalignment, two coils, like a transmitter and receiver coil, which you have seen here in the FEMM analysis, have, for example, a 0-degree misalignment, angular misalignment. If this misalignment is 0 degrees, the transmitter and the receiver are parallel. If the parallelity will be changed, so that means we have an angular, for example, of 40 degrees, we can see in the simulation here that by 0 degree, the coupling between these two coils is 0.95. And if we increase the angular, the coupling is dropping down around to 0.4. That's more than half of it. So that means only by changing the angular misalignment, the coupling factor is just a half of it. That means the efficiency is also dropping down. The coupling factor is depending on the coil size ratio. As we can see in the formula, that the coupling factor is directly according to this area's effective areas. For example, we have here as a transmitter a A11 or A10 coil. This A10 or A11 coil we can combine with 3 different receiver coils, for example, and you see if the area is 1 by 1, the coupling factor is 0.8. If we reduce the area to the right-hand side to 1 to 2, the coupling factor is dropping down by around about 20%. We can see here again that the coil, which is mentioned by 1 is a dimensioning of 40 by 40 millimeter, and the smaller one, for example, is 29 by 29 or 26 millimeter round shape. In this picture, for example, we see the different kind of areas which is influenced the coupling factor and the Q factor. The Q factor example you can see here. If we use a solid ferrite, this is the left part with the 760, 308, 102, 210 in the end, and the Q factor is 50. And it uses our Litz wire. With this Litz wire, you can see the DC resistance and the AC resistance is very low. At the right-hand side, at the next part, for example, the Q factor is a little bit lower. And this also have an influence on the wire type, for example. And on the right-hand side, the coil is just using a single wire. The single wire and the very thin ferrite will have a very low Q factor and a high DC and AC resistance. As you can see, the DC and AC resistance is around about 4 times higher. What influence have this in the system? The system itself, if we are simulating from the before mentioned transmitter coil, is the A10 coil, and these 4 different coils as a receiver, we expect normally the coil with the best coupling will have the best figure of merit. So that means the Q factor multiplied by the coupling is the whole system efficiency. But you can see it is not the coil with the highest Q factor with the best figure of merit. No, it's the coil with the biggest area. So you can see the part with the 207 in the end, which will have the area of 40 by 40, have the biggest K factor with the used transmitter coil, and the biggest Q factor coil with the 210 in the end is 16% worse than the other one. Additionally, you can see the smallest part, or the smallest area, effective area, have a difference to the best one about 40%. This will be 40% less efficiency. Now we will have a look into the combination of coils. If we have a proprietary system, which is using a non-Qi system, you can use the same coils for transmitter and receiver. And if we combine them, for example, with the same size, you can see also here the Q factor of all parts are very high. And they have a very, very rough same of the coil areas. So the coil outer diameter is more or less the same, just the ferrite around is bigger. This will affect to the higher Q factor, which you can see here by 220, according to the 180, which is the round shape. This bigger ferrite with a different kind of Q, which affect to a higher Q factor, will affect to a total bigger FEMM figure of merit factor. In the end, the efficiency is getting higher. As these parts, as you can see, are very similar, the efficiency difference is not so high, and in the distance of 6 to 8 millimeter between these two coils, the coupling factor is in the range of 0.4 to 0.7, 0.6. But now we heard about that the ferrite material itself is also an influencing to the Q factor. So that means we have to check what kind of material we have to use. So the coil material itself is also impacting. So why? So in the end, we can for sure use a coil without any shielding. It looks like in the left upper corner that the field is around the coil and there is no shielding. Now we can include a shielding at the transmitter side, for example, and you can see that the magnetic field on the back side of the ferrite is more or less 0. So no effects for parts which are on the back side of the coil. Now we can also place a second coil on top of it. So that means the transmitter and the receiver coil, they are close coupled. The coupling is very good. And the magnetic field between these two coils are focused between of these very short distance. And around that two coils, this pair, the magnetic field is very, very low. We can place our other parts and our schematics and applications around it, like a battery or capacitors, which will be not influenced. So important is the core material, the ferrite material. What kind of ferrite materials we have in the market in general? These are not all of them, but these are 3 examples. For example, we will have a iron powder material, which is in the black curve. This iron powder material is used mostly for applications up to 400 kilohertz, but also the resistance losses are dominating. The second material is the red curve. It's a manganic zinc material. These are used mostly for inductors, transformers, which are working frequencies in 20 to 30 megahertz, and the most of the losses in the round of 10 megahertz. As you can see the curve after 10 megahertz, the curve is dropping down immediately. This last curve is a nickel zinc material, for example, which can be used for higher frequencies up to 60 megahertz or more. Also up to gigahertz ranges are possible. So for the wireless power transfer system, mostly nickel zinc and manganic zinc materials are used. Here I have taken out some 2 materials from the manufacturer Acme, and these you can see if you compare them that the permeability in one time is 800 and the other one is 2400. But that is not meaning that the high permeability material will always better. This depends really on what kind of working frequency you have, what kind of shielding you need, and for sure also the material itself have AC losses in the material itself. And the losses can be shown here as power loss, and the power loss at different kind of magnetic flux and different kind of frequencies are differing, and depending on what kind is the best, it's better to use one of these 2. We will have a look onto the permeability curves. As you can see here, very important is that the permeability mu prime at both sides are very stable, about the range from 10 kilohertz up to 10 megahertz. At the manganic zinc also the same. But which is differing is the mu double prime. The mu double prime curve shows the losses, the AC losses inside of the material. So depends on which kind of in which frequency we are working, this material must be chosen. So the power losses at, for example, the magnetic zinc in the range of 100 kilohertz, very low. Also the same for the nickel zinc. But the nickel zinc in this range, the permeability is a little bit lower. So that means the Q factor is also a little bit lower, or the inductance. And if the inductance is lower, so we have to choose, or we have to wind more turns to achieve the same inductance. So according to the ferrite material, it's important to have a look low loss materials and depends on your working frequency. I would like to show you an EMI measurement, which we did in our lab. Here we have a sensor as measuring the harmonics on the backside of a working receiver coil. As you can see, we used 3 different coils with 3 different materials: manganic zinc, nickel zinc, and iron powder. You can see here the first harmonics and the next ones, that the coil type 1 with a manganic zinc material have the lowest emissions. As you can see, the dBm is lower than from the green curve or from the blue curve. Also, this is a very important point. As you can see, this is an important point to choose the correct material. But the next thing is, we had a lot of questions about, what about I would like to choose a material with a different thickness, or as a plate over the hole, or more or less. In this case, we will have a look at different kind of shapes of the ferrite shielding material on the backside of the coil. As an ideal coil, we can see here a round-shaped coil with a outer diameter of 10 centimeter, 10 turns, and we have an inductance of 32 microhenry. As you can see in the picture, the magnetic field is around the coil, and it looks great, as on the backside we have no fields. Now, specific applications, they would like to have a hole in the middle. If we have a center hole, you can see that in the same parameters which we have before, the inductance is the same, no big change. But what you can see is in the middle of this coil, on the back side, the magnetic field is not green, not zero like before. You will have a magnetic field on the back side of your part, and that means you cannot place any components directly in the backside. But maybe you want to reduce the total weight of your part and of the system, and additionally, one possibility is to use stripes instead of a whole plate or whole ring of ferrite. You can see here for sure the same parameter, the outer diameter is the same, the turns are the same, but the inductance is dropping down from 32 to 25 microhenry. And you can see here also around the coil at the edges and on the back side, the magnetic field is much, much higher. Now we will see the same simulation, just not through the ferrite stripes. It's just on the middle of it. And you see here again that the magnetic field on the backside is much more than which we are expecting and which we are not using as, for examples, if you're placing a battery on the backside to charge, then you will have a lot of eddy currents. As a second coil material, which we have here, is the wire types. The wire types, we have in our portfolio, for example, 4 different types. These 4 different types is just an example. We have much more, but there are these most used are the single wire, the bifilar wire, a Litz wire, or a Litz wire in bifilar mode. What are the advantages or disadvantages? The single wire is very simple, it's cheap, and you can use it every time to any shape. The second one is the bifilar. The bifilar is the same as the single, just we use 2 single wires in parallel and wind them together. So that means the diameter is double, the height is low, and we will have a low RDC, which will affect a lower AC R, so low AC resistance, as we will have a bigger cross section of the copper and a lower height. The Litz wire is for sure a better solution. If you would like to reduce the skin and proximity effects, it's more flexible, but for sure a little bit more costly. The next step will be for high power applications. You are winding a Litz wire bifilar. This is the same as before. It reduces the skin and proximity effects. It's more flexible, and the diameter is also lower and the height is lower, but it's more or less double in the costs. For the coil tuning, we can do that for sure. Every customer have different kind of needs and applications. In this case, there are customer-specific coils needed. The question is, can you do that? Yes, we can do it for sure. What you have to do. you have to go to our website and to go to the custom coils on the right-hand side, click on it, and you will go to the inquiry sheet. At the inquiry sheet, you have to fill in some basic parameters, which could be the input voltage, the frequency, the currents. Maybe you have an idea of your inductance and tolerances or the DC values and Q factors. Additionally, the mechanical specification parameters are needed for us, like the length, the width, the height, what maximum currents you see. Do you have a SMT or THD part? Do you want to have a very thick ferrite or more flexible? All these informations are needed that we can build up and simulate your customized part for your need. But there's always a but. Important is this process takes time. In this example, I'm just trying to show you the process, how long it takes that you will get a first customized coil. In the beginning, for sure, we will get this request by the inquiry sheet. Then we need round about 5 working days to do some simulations and checking what is possible and what's not possible. Then you will get a feedback from our side and have time to evaluate, is this the correct solution in your system? If this is correct, we will go into the production of tooling, of ferrite shieldings, of the winding, of prototyping. All this depends on the complexity of the part itself. It's 3 to 6 weeks, could be less depending on if we can use, for example, toolings which are available. Then we do assembly and the samples will be ready. After that, the parts will be delivered from Asia to Europe. In our lab in Munich, we will do the first tests and give you the feedback if we have these simulated and calculated results which we expect. After that, we can deliver to you globally in any place, normally with Express, so that you will get it in 3 days, best case. Totally, we will see this is a time frame of round about 8 to 9 weeks. Optimizing the coil, points to consider. Important is, if you are looking into the coil consideration, is you have to have use the largest possible coil which will fit in your housing and application. Important is to keep the distance between the 2 coils in the range of the maximum efficiency. As shown before, the coupling factor and the Q factor are important. Additionally, the misalignment, keep it as minimal as possible. So keep the design engineer in the beginning of the project in your team. Choose the best matching coil combination, as the coil combination will give you the best efficiency with the effective area which are used. Be aware of parameters which influence your performance. For example, have a look into the Q factors, have a look into the materials and wires, where we can assist you to find the best parts which are fitting into your application. And how we can do that? We have the products you need. As mentioned, we have customized coils, which can be done for you for sure. And we have the broadest portfolio in the market of standard products. If you would like to have a look into this kind of products and more information what we have, please go to our website and visit www.we-online.com/power, where you can find for sure all relevant informations and custom coil requests formula. I would like to thank you for your attendance, and if you have any questions, please let me know. Thanks a lot.